My name is Jay. I'm a PhD student in mechanical engineering working with Professor John Leonhardt. Along with our collaborators at Mastar Institute led by Professor Hassan Arafat, we are developing efficient membrane distillation systems for purification and concentration applications. Separation processes are really common in the industry. These can be for purifying streams of interest. For example, a beverage company might want to concentrate their juices or cola before transporting this out. Or it can be for, in the pharmaceutical industry, to produce ultra-pure water that can be used for the process. Sometimes you also want to concentrate your waste streams before disposing them in order to reduce the volume of disposal, and this is the case, for example, in hydraulic fracturing produced water, as well as textile and mining industry produced waters. But separation processes also take a lot of energy, and a lot of these processes do have waste heat or heat that's produced that needs to be dissipated. So a theme of this talk is to focus on whether we can use waste heat to affect some of these separation processes. We've decided to focus on membrane distillation to do this because it can use low temperature waste heat sources, and also because it's modular and can operate at several system sizes. Unlike some of the other technologies such as reverse osmosis or multi-stage distillation systems, it operates at atmospheric pressures and does not require high vacuum or high pressure pumps. Therefore, it has a simple design. But one problem with the existing membrane distillation modules is that the energy efficiency is not as high as the conventional technologies in this field. Our innovation bridges this gap in terms of energy efficiency and makes membrane distillation really competitive for these applications. So how does the process work? Membrane distillation is basically distillation through a hydrophobic membrane. Unlike normal distillation, you don't have boiling and condensation. Instead, you have evaporation and condensation. This means your process stream can only be 40 to 80 degrees Celsius or much lower than the boiling point at ambient pressures. You have a hydrophobic membrane that prevents liquid water from passing through, but allows vapor to pass through. A contaminated stream is heated, and as it flows through, the vapor passes through, it can condense on the other side as a pure stream. The membrane manages to make the system extremely compact with the evaporation and condensation happening within a few micrometers of each other. This membrane would be put into a system along with a condensing surface to enable heat recovery. So I'll go through the process schematic here. The process stream would enter on the right across a condensing surface. The condensation energy is transmitted into the stream, thereby preheating it, before it goes through a top heater where further energy is added. Finally, this stream would then flow on the left over a membrane. As it flows, vapor of the solvent leaves, and then the stream becomes a concentrated, cooler brine that can be disposed. And this condenses in the gap between the membrane and the condensing surface and is recovered as product. The way we've managed to improve this technology is by having models that predict the bottleneck. Conventional wisdom was that the gap needs to be insulating enough to prevent losses. But then we realized that going against this conventional wisdom, by adding materials in the gap to increase the conductivity, we can improve the overall heat regeneration and improve the energy efficiency as well as flux. Using funding from the Deshpande Institute grant, we've set up a foot-by-foot experimental setup in the lab. I'll be discussing some of the results. The setup performs exactly similar to the module shown before. We have fluid entering on the right side, going through a heater, going to the left side where it becomes concentrated brine. So what are the results? On the left, we have energy efficiency versus system size, comparing our new design with the conventional membrane distillation modules. You can see that over a wide range of system sizes, there is a two-fold increase in energy efficiency. This means you need lesser energy per unit of water to be treated or produced. At the same time, we also see the water flux as a function of temperature comparison between the new design and the conventional one. Again, a two-fold increase in water flux is also observed. This means your capital expenditure can reduce by a half. So these results have been published in an International Desalination Association conference, and we're also patented as well as submitted several drafts to the TLO at MIT. So how would all of this come together in a real system? Let's take the example of hydraulic fracturing. Oil wells are sparsely located over a geographic area, and each of these wells would produce brine that needs to be disposed, but can also be stored on site for a while. The conventional method here would be to truck out all this water into a common treatment facility or truck it out directly to disposal. By having a system that is tunable in terms of reducing the capital as well as the system size required, we can fit in a membrane distillation module into a mobile truck that can go to each of these wells and enable on-site waste regeneration as well as reducing the volume of waste. So in effect, we'll be having a lower capital investment per well because one system can handle water from all of these different wells, as well as reduce the volume of waste that needs to be trucked out by up to 50 or 70%. In conclusion though, so the membrane distillation system is customized for simple and compact operation at ambient pressures, producing purer waters and managing to use saltier brines. We are capable of harnessing waste heat sources. For example, at the oil well, there are gases that are burnt that are not used. We can use those sources. And our innovative design enables reduction in either capital or operating expenditure or any combination thereof. And we are really excited about a wide range of applications for this technology and are looking forward to talk to you about it over the coaster session. Thanks a lot.